Alright, today we get to talk about the chain rule. This has to do with taking derivatives of functions that are made by composing simpler ones together. For example, let's say we want the derivative of sine to the 50th power of x. Remember, that means sine of x to the 50th power. It's just a shorter way of writing it. Okay, so what's the derivative? Well, what does the derivative mean? It's a rate of change. How fast is y changing compared to x, right? i.e., what's the slope of the graph, or etc. So, to take this derivative, we're going to split the function in two, decompose it, just like we did in Chapter 1 with functions at the beginning of the semester. Y is something to the 50th power. I'll call that something u. And what is that something u? It's sine of x. So y is equal to u to the 50th power, and u is equal to sine of x. That makes the derivative of y, if I think of u as the variable, 50u to the 49th. So dy du is 50 times u to the 49th power. The derivative of u, thinking of x as the variable, is the cosine of x. The derivative of u with respect to x is cosine x. Again, what do these derivatives mean? Dy du is measuring how fast y is changing compared to u. And du dx is measuring how fast u is changing compared to x. Now, let's step back a minute and think about something else, which is related, but it won't sound like it at first. Let's say I know someone named Alice who works twice as fast as a guy named Bill. I also happen to know that Bill works 3 times as fast as Carol. So how much faster than Carol does Alice work? How fast does Alice work compared to Carol? Well, Alice's rate compared to Carol is how fast Alice works compared to Bill times how fast Bill works versus Carol. So Alice's rate compared to Carol is the product of the other two. 2 times 3, or 6. And if you think about it, if Alice is twice as fast as Bill and Bill is 3 times as fast as Carol, then Alice should in fact be 6 times as fast as Carol. Okay, so that means if I want to measure rates compared to different people or different variables or whatever, I need to multiply in some way. So let's look at it back to the original problem. If I want to think about how fast y changes compared to x, I can do that by multiplying how fast y changes compared to u times how fast u changes compared to x. In derivative terms, that's dy dx equals dy du times du dx. And then I just plug in. Dy du is 50u to the 49th, and du dx is cosine x. Those were the derivatives I found up above. Now, of course, my original problem didn't have any u's in it, so I'm going to replace that u with a sine x. So 50 times sine of x to the 49th power times cosine x. And I'll just rewrite that in the way we usually do. 50 sine to the 49th of x times cosine of x. That's the derivative of y. Here's another way to express what we just did. This is just a different notation. If I take that function, sine to the 50th of x, I want to write it as a composition of functions. Again, this is like we did at the beginning of the semester, and you had to do something like this on the first test. I can write it like so. F of g of x, where f of x is just x to the 50th, and g of x is sine x. Take the derivatives of both of those. They should look familiar. And now I want to know what's the derivative of f of g of x, that is, what's the derivative of that original composed function. Well, I know from the previous slide that it's 50 sine to the 49th of x times cosine x. In terms of g of x, that sine of x is g of x, and the cosine of x is g prime of x. So I have 50 g of x to the 49th times g prime of x. And hey, that 50 g of x to the 49th is 50 something to the 49th, which comes from an f prime. and the something is g of x. So it's f prime of g of x. It's putting that g of x into the f prime of x formula. Okay, so now I'm going to state those rules that we just found again. It's called the chain rule, and there's two ways to write it. So first of all, everything involved has to be differentiable, otherwise this won't work. But assuming everything's differentiable, if I have a function that is a composition of simpler functions, then its derivative can be written as f prime of g of x times g prime of x. That's what we just saw in the previous slide. Remember, a composition of functions, f composed with g means f of g of x. And this derivative formula from the chain rule, a good way to think about it or to say it to yourself is, this is the derivative of the outside at the inside times the derivative of the inside. F prime of g of x times g prime of x. Okay, there's another way to write it, the way we did it first, using Leibniz notation. That's the way of writing derivatives with all the d's and fractiony things. Okay, so if y is something involving u and u is something involving x, then dy dx, the derivative of y with respect to x, what did we get? It's dy du times du dx, the derivative of y with respect to u times the derivative of u with respect to x. That way of writing it is really nice and easy to remember because it looks like we're just multiplying fractions and canceling the du, right? It just looks like we're canceling the du. But that's not what's going on, right? Those aren't actually fractions. Those are limits. Each one of those is a derivative, which means it's a limit. So it's not as simple as just canceling the du's, but it looks like we're canceling the du's, and that makes it nice and easy to remember. Okay, so that's the chain rule. There's two ways to write it. And in fact, it works even if you compose more than two functions. Instead of just f composed with g, I could have f composed with g composed with h and write out the chain rule. Or I could have y as a function of u as a function of x is a function of t, and then find dy dt by multiplying dy du times du dx times dx dt. We'll see all this stuff in class. The point is the chain rule can be written these two different ways, and that you can do it with more than two functions if you need to. We're going to look at one more example. Let's find the derivative of the square root of x squared plus 1. We're going to do it two ways, one way using the Leibniz notation, one way using the function notation. I don't care which way you do these, you just need to pick the way that makes sense to you, that you like best. It's okay if you sometimes use one and sometimes use the other, or it's okay if you just pick the one you like best and always go that way. So here's the Leibniz way. I'm going to call this function y, and I then write it as y is something involving u, and u is something involving x. So y is the square root of u is x squared plus 1. When I combine those, I get the function I want. And I have to take derivatives of both of them. So you should remember from the derivative formula thing that the derivative of the square root of u is 1 over 2 times the square root of u. Or if you don't like that, you can think about the square root of u as u to the 1/2 power and find its derivative that way. It works out the same. The derivative of x squared plus 1 is pretty easy. It's just 2x. So what is the derivative of the square root of x squared plus 1? Well, it's dy dx. That's what we're finding, the derivative of that y thing, thinking of x as the variable. The chain rule says that that's equal to dy du times du dx, and now I just fill those in. There's dy du, and there's du dx. And then I'm going to replace that u with what it equals, x squared plus 1. So I have 1 over 2 times the square root of x squared plus 1 times 2x. I can cancel some 2's and write it slightly nicer as x over the square root of x squared plus 1. And there's my answer. Okay, now let's do the same thing but using function notation. So the thing I want to take the derivative of is x squared plus 1 square root of all that, and I want to think of that as f of g of x. So the inside function, g of x, is x squared plus 1. The outside function, f of x, is the square root of x. And if you compose them, you do get the square root of x squared plus 1. Take their derivatives. And then I also need to know what f prime of g of x is. So that's f prime of x, but instead of x, I put g of x. And then I replace g of x with what it equals. So instead of 1 over 2 root x, I have 1 over 2 root g of x, and that means it's 1 over 2 root x squared plus 1. So what's the derivative of this composition of functions? Well, the chain rule says it's f prime of g of x times g prime of x. There's f prime of g of x, and there's g prime of x. F prime of g of x times g prime of x. Again, I can cancel the 2's and write it more nicely, but there's my answer, and it's the same answer as it should be. This is just two ways of writing or thinking about the exact same procedure. Notice that both of these used the chain rule, just different forms. Okay, I want to point out that eventually you don't have to do quite as much writing. Once you get used to doing this and you've done it a bunch of times and you're feeling more confident, you start doing things like the following. Okay, so I will sort of narrate what goes on in my head and show you what I write. I want the derivative of the square root of x squared plus 1. Well, that's the square root of something, and I know that the derivative of square roots is 1 over 2 times the square root. So I'm going to get 1 over 2 times the square root. But instead of the square root of x there, I'm going to fill in whatever was under the square root to begin with. That's the derivative of the outside, the derivative of the square root part. Then I need to multiply times the derivative of what's inside. That's the derivative of x squared plus 1. That's 2x. So I have the derivative of the square root stuff times the derivative of what's inside. And so I get x over the square root of x squared plus 1. Same answer, yay. Okay, so you don't have to do all the writing if you can kind of keep track of inside and outside functions and so on in your head. But at least at first, if you haven't done this before especially, or if you're worried about making a mistake, it's best to write it out. Okay, that's the end of the video. I will see you in class, and we'll do lots and lots and lots of problems using the chain rule. See you there.